Okay, welcome back, everyone. We're going to get on to chapter one, activity three this time. I'm just going to skip number two, small activity unit two here, and do three first, and then tomorrow we'll do two. So I think they need to be a little bit reordered here. We finished 1.1 yesterday, talked about radical expressions and simplifying conjugates and working with some rational expressions. So we're going to talk about Unit 1, Activity 3 today, rates of change, and this really builds on a lot of work that you did in advanced functions. So it's going to be a relatively quick lesson and talk about just from a different perspective rates of change. Okay, so we're going to get into, and again, I hope you remember how to find the PDF work that's under Unit 1 Materials, and we're on to rates of change, average rate of change, and instantaneous rate of changes PDF right here. If you need to click on that and download that, and it's going to model, I'll walk through the lesson, and it's going to model the online course right here. Okay, so here is our Smart Notebook lesson that we can download. Okay, so rates of change. Okay, a rate of change talks about practical relationships that involve interdependent quantities. Okay, so two variables, the dependent variable and the independent variable here. The independent variable is x. Okay, we know that to be x. It can represent, in practical applications, it can represent things like time or height, elevation or length, some common examples that we've seen. The dependent variable, or y, represents quantities such as distance or volume or air temperature or area. And I sort of did a one-to-one correspondence here, so distance and time, right? Okay, distance and time, and volume and height, and we'll talk about some of these specific air temperature and elevation. Okay, so as the elevation changes, the air temperature changes, and the air temperature depends on the elevation. Okay, area and length, for example. Okay, so we talk about some of these examples up here. The volume in a balloon varies with its height above the ground, and air temperature varies with elevation. Okay, we often talk about how rapidly the dependent variable changes when there's a change in the independent variable. So let's use real quickly time and distance. So if I travel a distance over a certain time, okay, and I speed up and I increase that distance traveled, okay, over that short period of time, okay, that's described as a rate of change, and we talk about calculating a rate of change. You guys started to do this back in grade 9 when you talked about slope, and that's really all that is. Slope calculation is a rate of change calculation. When you got into advanced functions, you learned a couple of formulas and some concepts of rate of change, but in each case they all use the slope formula here. Okay, so that's kind of what we're talking about today, and going to work on a couple of examples here. Before we do that, we need to get two terms down, mathematical terms down. Okay, a secant is the first thing. Okay, and a secant is a line that intersects a curve at 2 points. Okay, so think of a parabola opening out, and a secant line shown with the blue line here in my diagram would intersect that curve at 2 points. Okay, a secant is a trigonometric term. Okay, and we're going to talk a lot later about trigonometric functions, but you guys can understand that a secant also has a relationship between lines on that intersect curves and functions here. Okay, good, we got that. Okay, a tangent line is a line that touches a curve at 1 point. Okay, and at this example, I use the same parabola. Okay, but I simply drew a tangent line, okay, that intersects or touches. Okay, let's not talk about intersecting, but it just touches a particular curve at 1 point, and that's represented on the blue line. Okay, got that straight? Secant, okay, and tangent. Okay, so we're going to use those definitions to develop our average rate of change. So an average rate of change formula is, like I said, a slope formula. You've noticed, okay, average rate of change, I'm going to use ARC for the abbreviation of average rate of change, or at times I'm going to use AROC, okay, for average rate of change. Okay, notice that it's a slope formula, delta y over delta x, here at y2 minus y1 over x2 minus x1, or f at x2 minus f at x1 minus x2 minus x1. Okay, or sorry, over x2 minus x1. geometrically, the average rate of change is the slope of the secant line, okay? Okay, and that's why we talked about what a secant was, and it's passing through 2 points. Okay, there's an animated GIF on the side here. The purple, okay, line, okay, is a secant and a secant line and average rate of change calculation for most of it, except right there, it's an average rate of change calculation. We're going to talk about, okay, finding the slope of this blue, or sorry, this purple line, okay, as we talk about, okay, average rate of change. So average rate of change has a variety of different formulas here. An average rate of change, we're trying to find the rate of change or the slope between 2 points that could be spaced apart relatively closely, but there's certainly 2 different points. Okay, this representation is not an ordered pair, it's an interval, okay, and that's the interval AB. Okay, so between the points A and B, I should be able to find an average rate of change, and that's would be found by using this definition here. Okay, so think of it this way: as the point B approaches A, okay, the secant line, okay, passes through A, and as we get closer and closer and closer, the secant becomes a tangent, and that's when it'll become an instantaneous rate of change. And we'll go over that in a few minutes. So it's always about slope calculations, okay? And think of average rate of change as finding basically just the average between 2 points. Okay, average rate of change, average between 2 points on an interval, in this case A to B. Okay, so as this gap between these 2 points A and B gets closer and closer and closer together, or the gap narrows, okay, so the point B gets really, really close to A, all of a sudden, back to our graphic here, I'm going to just scoot back here. Okay, see the gap between the two, the yellow point and the green point? Okay, so that gap is widening, widening, widening. It's getting closer and closer and closer. Right there, bang, right for an instance. Okay, right there again, right at that instance, is when those 2 points become 1 point. Okay, that's exactly what is discussed when we talk about instantaneous rate of change. So as the difference between the points becomes 0, the gap between the 2 points becomes 0, the average rate of change now approaches or becomes a thing called the instantaneous rate of change. So an instantaneous rate of change is a rate of change calculation at an instant, okay, at one particular instant. Okay, we can still use, the only formula we have is slope, right, the slope formula. So we can still use the slope formula. Okay, f at b minus f at a all over top of b minus a. But we have to understand that if we're using the instantaneous rate of change, that gap between A and B is really, really, really small. Okay, sometimes we use a thing called the limit notation, and we're going to spend later in this chapter talking about limits. Okay, but as B gets really close to A, that's the limit notation here. That's the LIM stands for limit. And as B gets really close to A, or as B approaches A, we get, okay, this approximation, and we call it instantaneous rate of change. Okay, another way to talk about instantaneous rate of change is use h as 0. Okay, so h is a height between maybe 2 points, okay, that are really, really narrow, that aren't very far apart. Okay, so I can find an instantaneous rate of change as h approaches 0 if I add, okay, that at a particular point, f at a, and then add that little bit of extra height, okay, or that value of h onto A and find a different value. That's like the y2 value here. Okay, I think I'm making this a lot more challenging or harder than it really is, because the formulas and calculating a rate of change, whether it's average rate of change or instantaneous rate of change, is actually quite easy. Okay, we'll work through a couple of examples here in a minute, but I just want to go back and revisit this graphic. Okay, so the purple line is an average rate of change. Okay, and then for an instant, the green line becomes, okay, this instantaneous rate of change, and we can calculate both of these things here. I know you've done this in advanced functions. Okay, so at this point, we'll just work through a couple of examples. Okay, now they're different. You'll be given different things when you're asked to find a rate of change. Sometimes you'll be given a graph. Okay, sometimes you'll be given a table of values. Sometimes you'll be given a function. Okay, an equation of a function. So if we're given a graph, okay, let's find the average rate of change, okay, on the interval -1 to 1. Okay, so the average rate of change, okay, on the function, okay, on the graph shown between the interval -1 to 1. So average rate of change, okay, I'm going to find, okay, the value of the function at 1, take away the value of the function at negative 1, because I'm going from negative 1 to 1, and that's going to be over top of 1, take away negative 1. Okay, so I need some values here. So I go to my graph and read the value of the function at 1. Okay, so the value of the function at 1 is approximately right here. That looks like it's... Okay, so the value of the function at 1 is negative 3. Again, I'm going to subtract the value of the function at negative 1. Okay, it looks like it's negative 1. Okay, and then 1, that'll be a plus 1. So I've got negative 3 plus 1 over 2. Okay, negative 2 over 2. Okay, or negative 1. So the average rate of change is negative 1. Now, that average rate of change is the slope of that line that I just drew, the slope of the secant line. Okay, now if I did old school calculating slope, I'd get that. Okay, let's find the average rate of change in the interval 0 to 2. Okay, so the interval 0 to 2, the average rate of change, I'm going to call it AROC this time. It was from 0 to 2, so I need the value of the function at 2, okay, the value of the function at 0, and it's over 2 minus 0. Okay, so I can go and get the value at 2, approximately here, okay, and then the value at 0, approximately here. That looks like it's 2 and negative 1, and it also looks like it's 0 and negative 1. Well, okay, that's going to be a horizontal flat straight line. So what did I say? The value of the function at 2 is negative 1, and also negative 1 over 2. Okay, that'll be negative 1 plus 1 over 2, or 0 over 2, or 0. Okay, and that certainly looks like my slope. Okay, my secant line is 0. Okay, and this slope is 1 because of the average rate of change. So when you're asked to find average rate of change, just think of slope, calculate slope. Okay, now let's estimate the instantaneous rate of change at x equals 0. Okay, I use the word estimate here because I don't have an equation. Okay, I don't have a function, and I'm just simply reading, okay, values here. Okay, but what I can do, okay, at 0, okay, is right in here. I want to try and find, okay, the slope of this tangent. Okay, that would be this calculation. Okay, well, that's a tough one. That's really a tough one to do here. Estimating is very difficult, and okay, when I have to find the average rate of change given a graph, sorry, instantaneous rate of change, okay, I just have to estimate. Okay, and it can be a very difficult. Okay, now if I wanted to use a formula, okay, I'm going to show you why. I'm not going to calculate it, okay? Okay, I'm going to show you why, how I'd have to do this though. If I want to find the average rate of change at x equals 0, I'd still use my function, okay? But I'd use a value very, very close to 0, okay? So let's go 0.001, and then I'd subtract f at 0, and then I do the difference, okay? So this would be, okay, I'd have to find the value of the function at 0.001. Well, that's difficult, okay? At 0.001 would be right in here, okay? I think it's slightly, a little bit over negative 1 here, okay? So it's a little bit over negative 1, so let's go like negative 1.1 maybe, okay? F at 0, okay, is negative 1, and that would be all over. Okay, this starts to fall apart here simply because, okay, I said it was an estimate, and this is just a guess, right? Okay, I just read that value from my graph. Okay, I had no idea. I don't have a function to verify that value. I'm going to continue with this calculation though. Okay, I'm going to continue with this calculation. So negative 1.1 plus 1, okay, would be a negative, okay, 0.1 divided by 0.001 here. Okay, and that's, okay, going to be a pretty large negative number. 0.1 negative divided by 0.01 is like negative 100. Ooh, steep. What I don't think it's negative 100, but certainly it's a steep negative, okay, tangent line. The slope of that tangent line is a steep negative number here. Okay, all we can do is estimate, especially when we have to read a graph. Okay, we have an idea of what it looks like though. Okay, okay. In the online class, D2L lesson pages, there's some really two good videos. They're kind of cartoonish style, but they're exceptional videos on approximating the average rate of change, calculating the average rate of change of a function, and then approximating the instantaneous change of a function. I would suggest you watch them. I'm not going to show you the videos here during my online class or my online synchronous lesson here, but I would strongly encourage you to go and watch the two videos if you need further examples to watch. Okay, let's use different calculate average rate of change. Okay, given an actual equation here. All right, so this is going to be. I like to use equations. Okay, certainly when I'm given an equation, it's much easier to work with. Okay, so I've got to find the function at 3, function at 1, and then 3 minus 1. Okay, so the function at 3, I've got this to be 3 squared is 9 minus 6. It would be 9 minus 6. Subtract. The function at 1 will be 1 minus 2, and that's all over 3 minus 1 is 2. So I've got here 3 minus negative 1 over 2. That looks like it's 4 over 2. 2 is my average rate of change between. So the slope of my secant line is 2. For b, I'm just going to use a different function, and I have to find average rate of change here between the function at 1, I always do the second point, minus the function at 0, over 1 minus 0. Okay, so now I've got, I'm going to substitute 1 into my function here. Okay, so f at 1 would be 0 over 3, and f at 0 would be negative 1 over 2, okay, and that's all over 1. Okay, so basically I've just got 0 plus a half over 1, or 1 half. Okay, and my slope of my tangent, the slope of my secant line between the points 0 and 1 is, say, 1 half. The average rate of change is 1 half. Okay, I didn't ask you to do an instantaneous rate of change for this example. Okay, a common question might be, okay, instantaneous rate of change. Let's get a function, x to the power 3 minus 2x, okay, and it would be at x equals 2. That's how an instantaneous rate of change question would look like. Okay, I'm giving you 1 point. Okay, I'm giving you a function. Okay, so we'd still use the formula, right? But we just go a little bit off that point at x equals 2. I'll do one in the next and last example here. I think we're going to do b, instantaneous rate of change. Okay, so here's our function. A pebble is dropped from a cliff 80 meters high. After t seconds, the pebble is s meters above the ground, where s is given with a function, and we go, okay, time is between 0 and 4 seconds. Okay, so let's calculate the average rate of change. How fast is this pebble moving? Between 1 and 3 seconds. Okay, so I'll just use the abbreviation AROC this time. Okay, and at times you'll see this notation in square brackets between 1 and 3, and I'm going to have to calculate s at 3 minus s at 1, and that's all over 3 minus 1. All right, s at 3, I'm just going to have to peek to my formula here, my sheet. S at 3, I get to be 80 minus 45. Okay, and that was just substituting 3 in here and 3 in here. Okay, and then I have to take that, take s at 1 away, and I've got s at 1 was found by substituting into my given distance formula. Okay, 80 minus 5t squared. When t equals 1, I get 80 minus 5, an expression, and this is all going to be over 2. Okay, so 80 minus 45, I got 35. Okay, and then I have subtract 75 over 2. okay, which I get to be negative 40 over 2, okay, or negative 20. Okay, and that's an application question, so I need units on here, and it looks like it's, okay, meters in the top, right? Okay, this is meters, okay, and this is time, okay, because it's S, right? S is in meters, okay, and this is time in seconds. Okay, so our units would be meters per second, and that's velocity, right? Velocity, meters per second. So average rate of change in this particular example is a average velocity question. Okay, instantaneous velocity. Let's do instantaneous velocity. Okay, so here's a good instantaneous rate of change question. So instantaneous rate of change is going to be found at t equals 2 seconds. Okay, so my formula here is going to be s at, let's go 2.001 minus s at 2 over top of 2.001, take away 2. Okay, I'm going to stop here, pause this for a second here, and talk about this little decision here. We haven't done this one yet. Okay, so at a particular point, at an instance, in this case t equals 2, I still use my point 2, but I use a point really, really, really close to 2. And I've chosen just arbitrarily 2.001. Okay, I think that's doable. If I go to 3 decimal places, I think that's doable. If you choose 2.1, although you're correct, your answer may not be very accurate. So I think we could go better. Okay, if you use 2.01, okay, that's better. Okay, but I think we could even do better, and it may be pretty accurate, much more accurate than 2.1, but not as accurate as 2.001. I'm going to choose to go 3 decimal places. So in this particular example, the second point will be 2.001. That's at 2 and slightly above 2. Okay, in advanced functions, if this was taught to you properly, advanced functions, when you talked about an average rate of change, you would have realized that you could have had other choices. You could go 2 and then slightly below 2. So you could have an instantaneous rate of change at 2 and then subtract s at 1.99 if you wanted to. Okay, that's still an instantaneous rate of change at 2. So we could go slightly below the point, we could go slightly above the point, or we could go in between the point. Okay, so we could go 2.001 minus 1.999. Okay, so that the point 2 sort of gets in the middle here, and the bookends are the intervals. So our choices, I'm just going to put them over here to 2. We could go 2 to 1.999, and then we could go from 2.001 to 1.999. Every one of these types of decisions or ways we do this, okay, is an accurate way to calculate an instantaneous rate of change. Okay, so this is slightly above, this is slightly below, and this is right in the middle. Now, I typically decide, and if I have to make a decision, I try and make a smart decision in math. I typically don't do this, okay, because there's a reason why I don't choose to do this if given a choice. Okay, is that I have 2 harder calculations to calculate, right? I have to find the value of the function at 2.001 and also find the value of the function at 1.999. So that's a little bit more challenging. I might be more apt to make a mistake. Okay, so I'm going to narrow my work down here. So that leaves me with, okay, this choice or this choice. I tend to always go the point and then slightly above the point. I just find it makes more sense, like I read things like that left to right here, okay? So I always read my functions left to right. So I'm at the point and I go slightly above the point. Okay, so let's go stick with this calculation here. I'm going to just change my pen back to black, okay? And I have to cheat. So S at 2.001, I got that to be 80 and then minus 20.020005. Okay, and that's just calculator math, and I'm going to write all my decimals, okay, in my formula in order to be really accurate. Okay, S at 2, the easy calculation, turned out to be 60, and then that's going to be 2.001 take away 2 is just my decimal. Okay, that leaves me with, again, 59.979995 minus 60. Okay. Carry all your decimals. If you're just working on your calculator and crunching numbers, carry all your decimals. Okay, now we have negative 0.020005 divided by. Okay, I'm going to stop right here. Okay, it's a negative. Okay, the numerator is a negative. Okay, we're going as I move from 2 seconds to just a little bit above 2.001 second. My particle, or what is it? A pebble. My pebble is decreasing, right? And this is delta. This was delta y, or the distance, right? The change in distance. The negative represents that it's dropping, okay, and that makes sense here, and that's why we're going. Not only is it dropping in distance, it's also decreasing, or the instantaneous rate of change is going to be a negative value, and I get negative 20.005, and here's where I round off. Okay, round off at my final answer, I get negative 20 meters per second. Okay, that has a familiar ring to it. Okay. The average rate of change between 1 and 3 was negative 20 meters per second, and the instantaneous rate of change at 2 was negative 20 meters per second. Okay, well, 2 is the average part in here, the average point between 1 and 3, right? So on continuous, nice, smooth, continuous functions, that might very well be the case in a lot of situations like that. Okay, there are some homework questions that I want you to do. They are here. Okay, there's also a mid-chapter review if you think you need more work, but maybe not do the mid-chapter review until we do tomorrow's lesson 1.2. Please don't forget to go and watch the 2 videos and work through this lesson. This lesson modeled pretty much the Smart Notebook video that you're watching here now. Okay, although there is this average rate of change of a function, and then instantaneous rate of change. Please make sure you know the difference between average rate of change and instantaneous rate of change, how to calculate the 2 different rates of change, and understand that for one, the average rate of change, it's the slope of the secant line, and for the other, the instantaneous rate of change, it's the slope of the tangent line. Okay, good luck. As you work through homework, my homework solutions are posted right in this area here, homework help. Okay, thanks, and good luck with this one.